Hello, this is Tony Nichols, co-founder and Chief Technical Officer of Great Ideas, and this video is part of our enterprise architecture with examples using Microsoft.NET Blazor, Azure, and Great Ideas Trellis Spark. And in this presentation, we're going to be talking about data architecture. So in this video, we're going to be giving you an overview of what data architecture is. Our primary focus is going to be securing access to data both at rest and in motion. So we need to answer a few fundamental questions. What do we mean by data? How do we improve the quality specifically of record data? How are we going to secure data? And we're also going to look at an implementation called Data Agnostic Services, which shows us different ways of actually securing and maintaining access to data. As ever, we're going to be using this as a high-level overview and then doing a set of deep dive videos on each of these topics. So the first question we need to ask is, what do we mean by data? So most people will immediately jump to the idea of record storage. So this is the storage of information about individual entities. So things like customers, vehicles, people, insurance policies, patients. So a record essentially is a set of aggregate fields that correspond to a specific entity. And typically these records are stored in relational databases and more recently in what we call document or NoSQL databases and so on. Another sort of data is what we would describe as file storage. So this would include things like Word documents, spreadsheets, images, PDF files, etc. So these are digital files stored in some sort of file or folder structure on electronic media. And then we have other categorizations of storage, which are essentially semi-structured. So things like email servers, where we're storing emails, identity management systems, where we're storing information about users, passwords, tokens, security certificates, etc. And also log information. So logs where essentially we're maintaining a set of status information over time relating to how something is working. So we have three broad categories: records, files, and what we're just putting into the category of other. Now, one interesting thing about data is that for file storage and most other storage, these storage mechanisms are essentially data agnostic already. So if I'm basically saving an electronic file on a disk, then it doesn't really matter to the file storage mechanism whether that disk is a Word document, an Excel spreadsheet, an image, or anything. It's essentially I am storing a sequence of bytes on a disk. And similarly with things like, say, emails, it doesn't matter what the email is about, it doesn't matter whether or not it has attachments, it doesn't really matter how big the attachments are, we're just storing information essentially agnostically. Record storage is different. We are moving towards a movement where we're doing some document storage in NoSQL databases where we are using agnostic storage mechanisms such as XML and JSON. So we are making a move towards data agnostic record storage. But the truth is that the majority of information related to vehicles, cars, people, etc., is still stored in tables in relational databases. And those storage mechanisms at the relational database level are essentially agnostic, but the actual formats in which we store these entity records are not. So if we want to store information about a customer, it goes in a customer table, and that is completely separate and distinct from information about vehicles, which would go into a vehicle table. So although the basic underlying storage mechanisms in all of these cases are by nature data agnostic, the large majority of record storage isn't. So one of the things we're going to be looking at is how do we bridge the gap on record storage to move to a more data agnostic format. So a primary consideration of data architecture is to make sure that we improve or maintain the quality of the record data that's being used to power our enterprises. The issue we have in most organizations is that we still have lots, and I'm talking tens, sometimes hundreds, of applications where we have data that's been encapsulated within the application. Let's take a simple scenario. I have application A where my user enters customer information. I have application B where my user enters order information. I have application C where my user is fulfilling those orders. And then I have application D where I'm providing invoices and collecting payment information for the fulfillment of the orders. So a user who's actually flowing through the task of placing an order and invoicing the order after fulfillment is signing into application A to create and maintain customer information, application B to create and maintain order information, which they then have to link to customer information. They're going into application C to create and maintain fulfillment information, which again may depend on order and customer data. And finally, application D to generate and record payment for invoices, which again needs order, invoice, and customer information. So lots of places where, for example, we're storing customer data. So this is an example of classic swivelware. To complete one business process, users are signing into multiple applications, re-entering or linking records across multiple applications, and whenever they do that, there is always the possibility that they're going to make a mistake. They're going to enter the wrong address for the customer. They're going to link the order to the wrong customer. They're going to fulfill the wrong order. So the problem becomes the number of data silos. The more swivelware we have to go through to implement a business process, the more likely it is that somebody somewhere is going to make a mistake, and that's going to disappoint customers, that's going to introduce costs, that's going to reduce profitability. It's not good. So one thing as data architects we want to try and do is reduce the number of data silos and reduce the amount of swivelware in our enterprises. So ideally, what we want to be able to do is identify a single system of record for each type of data. So for example, if it's customer information, ideally the single source of truth is application A. Right, that's where the customer was created, and we're referencing it in applications B, C, and D. Well, that's not always possible. Sometimes the information I need in application A for a customer isn't the same as I need in applications B and C and D. Maybe the identifiers are different. Maybe the address field formats are different. So sometimes it's hard or even impossible to have a single system of record for each entity within your enterprise. And this is where we end up in this really big, extensive topic where we're talking about data integration. So how do I ensure that a customer in A is correctly represented in B, C, and D? Well, ideally, we would have real-time point-to-point, so P2P integration through some form of API and distributed transaction. So if I was in application A and I'm making a change, that the change to the customer in application A isn't committed and complete until the change is also updated in applications B, C, and D. And we're going to be doing a couple of video tutorials that describe some of the architectural techniques where we might attempt to do that. One of the big challenges that we're going to see there is what we describe as the integration hairball challenge, or the version control challenge. So each of applications A, B, C, and D are going to be working at a particular version level. So let's say I've completed my point-to-point integration, and at the time when this application was built and tested, version of application B was version 8. Let's say 3 years, 4 years, 5 years elapse, and version 8 is now no longer a supported product. I need to upgrade to version 11. Now, when I upgrade application B to version 11, I might now break my point-to-point integration across all 4 applications, and that's obviously going to be bad, right? Because it's going to be expensive, it's going to be risky, there's going to be a lot of time and effort in terms of actually fixing this. And then the next year, I might need to do it again when I upgrade application C. So point-to-point integration in real time, where we have distributed committing of data changes, is extremely rare in practice, and it's almost impossible to maintain. So the next level down is essentially models around what we describe as eventual consistency. So in eventual consistency, we're using essentially a queuing mechanism or a buffering mechanism. So when we change the customer information in application A, we might route that change to a message queue or an enterprise service bus, and then applications B and C and D would pick up the change from the buffer, make the appropriate change in their system, and if they changed customer information, they would go through the same process. They would write the change back to a message queue or a service bus, and then it would be picked up and copied across later. So we'll do a couple of presentations talking about buffering technologies. Two of the common ones are essentially around this idea of message queues or ESBs. Another one is essentially extract, transform, load of batch files, for example. The third option that is used in a few organizations, again, not very common, is the idea of entity synchronization layer. So essentially what we're doing with an entity synchronization layer, or ESL, is we're creating a layer where we are going to abstract the entities from the applications. So instead of the customer information being in applications A, B, C, and D, and some level of truth in each of those applications, what we're going to do is we're going to abstract the idea of the customer entity into the ESL. And the ESL, the entity synchronization layer, now becomes a fifth data silo, but it is the definitive source of truth for customer information. So what happens in this case is if somebody goes in and creates a new customer or changes a customer in application A, it writes the changes to the customer record in the entity synchronization layer. And the entity synchronization layer is then responsible for distributing that change across all of the other applications. So this, to a certain extent, gets around some of the version control issues that we have in point-to-point APIs, in that we've used the entity synchronization layer as a buffering mechanism to make sure that changes are correctly distributed across all applications. Again, we have an eventual consistency problem, but essentially it becomes a little bit easier to do it this way than using the ideas of message queues, ESBs, and extract, transform, load. So this is a little bit more of an elegant solution to the data integration problem, but we're still dealing with compromises. The other thing we need to consider is the quality of the incoming data. So if we have places where we have applications where data is being sourced from external vendors or other systems, then one of the things that we need to do as we bring that data in is to inspect the quality and cleanliness of that data. So, for example, in the case of a customer, we may have a field on there that says, this is the date field, this person has been a customer since this date and time. So the business rule, obviously, is, well, let's make sure that data is in the past, right? If I've got a customer record coming in where this is a customer in the future, then clearly I've broken the business rule that says customer since should be a date in the past. So one of the things that we need to consider is how do we assess the quality and cleanliness of data as it arrives before it's ingested into our applications. So again, we'll be doing a couple of videos related to ingesting incoming data sets. The next key topic when we consider data architecture is how do we secure the data under our control? We have to start with the assumption that data is the primary target for hackers. It's where the value sits in the application. Essentially, the hacker is going to try and steal the information, or they're going to try and encrypt it so that they can charge us a ransom to actually get our data back. And potentially a whole hybrid of attacks that sit somewhere in the middle of those two extremes. So one thing that we want to do is use our data architecture to define a set of common security standards and practices for how we store information of particular types, where we store it, how we store it, and essentially a lot of that is done within our technical architecture. So we'll be doing a whole bunch of tutorials around securing data, and we'll be dealing with a lot of that in our technical architecture tutorials. One of the overarching principles is that whenever we're looking at security, we want a set of overlapping and defense in depth. So essentially, we want to secure our data using multiple security systems with different authentication and authorization at each level. We want to try and make sure that we have granular access to information. So ideally, access to a record should be granted at record level. So if I'm a user, Tony, and I'm trying to access customer information, I shouldn't be seeing all customers. I should be seeing a subset of customers. And the only way that I can get access to a particular customer record is if I have been specifically granted access to that customer. So essentially what we're going to be looking at in terms of security standards and practices is a mixture of technology security approaches in our definitions of how to set up and secure data from a technological perspective. We're going to be looking at how to apply these controls within the application layer of our applications as well. So in our user experience, how do we guarantee that Tony is allowed to look at this particular customer record? But we also need to consider, again, using our overlapping and defense in depth approach, how do we actually secure that within the actual data at rest store as well? And again, because data is the primary target, we want to make sure that we build the biggest moat, the biggest walls, the most sophisticated, automated monitoring, detection, alerting, and response mechanisms around our data as possible. Because the one thing we can guarantee is that hackers are going to be smarter than us. They're going to find a way of getting through some of these systems. And the more we put in place, the more we keep them updated and patched, the lower our risk of a hacker actually getting access to data. So it's all about making sure that we put the best mechanisms in place, that we understand what those standard sets of security standards and practices are, and that we're applying them uniformly across our applications so that we don't have any gaps or holes in our security mechanism. So as you can imagine, we're going to be doing a lot of work in future presentations that address the need of securing data at each of the different aspects of the information, whether we're dealing with the data at rest, or we're dealing with data in motion between systems, or we're looking at data presentation to users, or we're looking at how data is being used in workflow. So the security of data is essentially a primary concern of data architecture. Now, the most modern approach for dealing with enterprise architecture is based around service-oriented architecture. And one formulation of a service-oriented architecture approach that we're going to be adopting in this course and is used extensively within Great Ideas is this idea of data agnostic services. So essentially, data agnostic services is a pragmatic way of implementing a service-oriented architecture framework. The key essence of the DAS framework is that instead of customer information being held in applications A, B, C, and D, as we've described above, is that the data is instead held in a system of record in the data at rest. And essentially, this is the ultimate form of an entity synchronization layer. We are going to take the customer information out of applications A, B, C, and D, and we're just going to have one customer record. It's going to sit at the data at rest layer. So essentially, this is the ultimate way of abstracting the data and making sure that there is only one system of record, one source of truth for customer information, irrespective of whether or not we're using the interface for A, B, C, or D to present the user with customer information or to provide workflow on that customer information. So within the idea of data agnostic services, we have either data presentation, it's being presented to users. We have data in action, which is data basically being manipulated as part of a workflow. So for example, if I have some automation related to order fulfillment, then the workflow would be in the data in action services. And those data presentation and data in action are considered in our application architecture overviews. And what we're going to be focused on in the rest of this presentation is data at rest and data in motion. So data at rest. So this is data that's being actually stored somewhere within our enterprise. And again, this is the primary target. If a hacker wants to get hold of anything, it's the contents of your databases. Okay, it's where the whole value of your enterprise is. If I can hold your enterprise data hostage, that's the thing that you're going to need to pay for. So since data at rest is our highest value target, it's also the thing that we need to protect the most. So if you think about the diagram, essentially anything that's accessing data at rest is going through at least 2 or 3 times the security boundaries of any other data presentation, data in action, or data in motion. Okay, so data at rest, you want to put the biggest, highest walls around it. You want as much security as you can throw at it. You want to restrict and secure any data flow across the boundary of any of the other service areas into data at rest. Essentially, you want to secure the data at rest services. Those are your fortress of solitude. That's the place that you really need to start your focus of security on. So within the data at rest, we're going to want to encrypt the data as many different ways as possible. So we encrypt the media that the data sits on. We encrypt the data itself. We want to make sure we're encrypting the backups of that information. So anything we can do to secure the data at rest repositories should be part of our standard architectures, and it should be one of the first things that we do whenever we add new information to the system. How are we securing that data? How are we going to make sure that only authorized and authenticated users have access to it? So again, we're going to be talking a lot about this in the technical architecture, but it also applies when we're looking at data architecture and application architecture. One of the things about data at rest is we also need to consider the availability of data as well. So ideally, we want that data available 100% of the time. So reality check is we'll never have 100% availability. It's always 99.99999 whatever a level. And we need to understand, how many nines do we need? How many nines can we afford? And what are the technology considerations to actually make sure that that data is available? And mostly we're going to be dealing with that in technical architecture, but there are some considerations that we will talk about when we look through data at rest architecture as well. A related topic is the idea of disaster recovery or DR considerations. So if we have data in a data center and the data center burns down or becomes unavailable for a reason, so there's a major power outage and it's powered down for a week, then how can we bring that information up in a secondary location? So disaster recovery, again, it's primarily a technical architecture, but it's something we also need to consider as part of our data architectures. Now, fortunately, most data at rest services are already data agnostic. So think about it, files, emails, things like Power BI, right? It doesn't matter what the data is. Those stores are already data agnostic storage. So we can just use that out of the box. We're good to go. Record storage can be agnostic depending on the storage format we're using. So recently, over the last decade or so, we've had the emergence of NoSQL databases using XML or JSON as storage mechanisms. And prior to that, we obviously had relational storage where records are stored in tables. So I'd have a table of customer information. Now, the problem with relational storage in customer tables is that if I have a customer who happens to be a corporate, then I might need different fields to a customer who is a private individual, and different fields to a customer that is a non-profit organization. And that may even be different to a customer that's a government organization. So essentially, the different types of customers would need different tables within our relational databases with different fields. And different types of customer basically would have different data sets. So although we are already moving in some respects to agnostic record storage in NoSQL databases, we still have a lot of record storage, which is very specific table storage, where we have a set of fields, rules, business logic built around the type and values being stored for each of those records. One of the things that we're going to look at in the data at rest for data agnostic services is how do we get the best of both worlds? How do we get the functionality and flexibility of a relational database, but the ability to use agnostic storage in XML and JSON formats in document storage? So relational and document databases are two extremes. One of the things that we're going to consider in this course is how do we achieve a hybrid that gets the best of both worlds. So essentially what we're going to be looking at in data agnostic storage for record storage is how do we build those hybrids? How do we get the best of generic storage using XML with the power and performance of a relational database when we're trying to query and read and process that information. So we'll be doing a couple of videos that talk to hybrid record storage. And then another related topic there is performance optimization. So one of the issues with a lot of NoSQL document databases, if I've got, let's say, 20 million vehicle records and I want to run a query to find all of the blue vehicles, I've got to go through 20 million semi-structured XML records to find 2 million blue vehicles. That can take quite a long time. So ideally, I want to be able to optimize the querying of that record storage to give me my blue cars quicker. So again, part of how do we build the hybrid, how do we build the best of both relational databases and document databases is something that we're going to be considering quite deeply in this course. And finally, for this overview, let's consider data in motion. So data in motion is where we have data that's either flowing into our application, our enterprise architecture, or it's flowing out of it. So it may be information that we're exchanging with third parties, with regulators, with customers, with suppliers, vendors, and so on. So we have slightly different security concerns when we consider data in motion as when we're considering data at rest. So with data in motion, we need to understand who is actually sending the data to us. So if it's incoming data, who is the sender? Is it a valid sender? Do we understand and know this person or not? And if it's going out, who is actually going to be receiving that information? So with security, what we need to be looking at is that the data is going to be flowing across a boundary. We're going to need to understand who is sending, who is receiving the data, what do we expect to be sending, what do we expect to be receiving. One of the key considerations, that again is a mixture of data and technology architecture, is making sure that data in motion is always encrypted, and that if we're going through a transport storage, so for example, if we're sending information through a message queue or a service bus, that the storage media itself is also encrypted. So one of the things that we're going to be looking at in terms of data in motion technology is how do we understand the identities of the parties involved in the communication, how do we encrypt the data that's being sent, and how do we ensure that only the sender and recipient have actually access to that information. So there are clearly two different types of data in motion we need to consider. So the first of which is inbound. So when we're thinking about inbound data in motion, then initially we need to have data being migrated into the system as we populate it. Very few of the systems we're going to be building are greenfields that have no customers, but typically the organization may have an application it's retiring, or it may be merging information from an application from an organization it's just acquired, and we need to be able to migrate that data into our application. So essentially the data migration is a one-off ingestion process. And we may also have ongoing data flows coming in. So we may be getting an ETL from a vendor of all of the services it's provided to our customers. And that may be through an ETL that comes in once a day. It may be through a REST API or other mechanisms. So essentially, when we're considering inbound, then we have two different classes of problem. We have initial data migration and ongoing data ingestion. And we'll be doing presentations on both of these topics in the future. Key things we need to be considering is validation and cleanliness of the information as it flows into our system. And we're also going to need to consider different mechanisms for how that information is brought into the system. How do we buffer that information so that we can validate and cleanse it before we incorporate it into our systems of record? How do we correlate information? So if I've got an incoming data stream, how do I actually put some sort of correlation ID around the records I'm ingesting so that if there's a problem with that ingestion, I can roll back all of the changes quickly and cleanly? When we're considering outbound data in motion, we have a different set of problems. We're not worried about the validation and cleanliness of data coming in, and to a large extent, we don't really care about buffering, correlation, and rollback of the information flowing out. When we're dealing with outbound communication, what we're really trying to do is essentially data loss prevention and exfiltration of information that shouldn't be going out. So one of the things that we need to make sure we understand is how do we understand and send the minimum amount of data to the recipient. So essentially what we're looking at here is we have a communication. We're going to take some data out of our system. We're sending it to a third party, send them the minimum amount of information they need to do the task. Related to that, we also need to be able to track what data we've sent out of our system as well. So that's the other part of outbound communication. We've got to basically pull together a data set that we know we can send to this trusted recipient. We know we need to encrypt that information, we need to send it via a secured storage mechanism, and we need to say, well, this is the data we sent at this date and time. So again, data architecture, we want to put together standard mechanisms for all of our data in motion, whether it's inbound, whether it's outbound. We want to make sure we're securing it properly, and we'll be doing a number of different tutorials on each of these subtopics as well.
To learn more about great ideas, products, and solutions, visit greatideas.com. That's greatideas with a Z.com. Thanks.